So, hello everyone. Welcome to one of the first sessions of SOSCQ, and this is our kickoff session for a new group, a subgroup under SOSC called as SOSCQ, which deals with the quantum computing side of open source. So, quantum computing is something you might have been listening around in a lot of blogs, news, or stories, right? So, what is it exactly, and why should you care about it? This session will deal basically about a small introduction of what is quantum computing and where can you apply it in your life. Can you use it right now, or can you have new possibilities with it? Everything will be, we'll try to kind of cover up with this. So before we start on with what is quantum computing, let's look at the brief history as to why it started and why did someone think of this. Okay, so the first person that thought of this was Richard Feynman. So Richard Feynman is a brilliant computer scientist and a physicist, and he was working on simulations. So the idea is when you simulate something, a physical system, let's say you're simulating molecules or you're simulating your materials, what is basically done is you convert a physical system into a mathematical model, and then you convert it back into you process it, and then you get your results. So Richard Feynman saw this as a limitation because at that time you did not have a lot of computation power, and even though Moore's law was there, he did not really trust on the computation that will take to complete simulation of huge molecules, which is true. Even though we have so much computing power right now, we cannot really completely simulate large physical systems. So his idea was, why not have a quantum system to simulate something that is inherently quantum? So whatever we have around us is actually quantum. So why not make a quantum system? Why are we using a classical system? So the classical system in this sense would be the processor that you have right now in your computer, right? So that we are classifying that as classical, and we are saying the new type of computers, the quantum computers, as quantum. So his idea was, why not have a quantum computer to simulate the inherent quantum nature, which is nature. So this was his famous quote, which is basically quoted everywhere around. Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical. So this was in 1981, and this had caused a lot of discussions around the technological sphere. Like, okay, this is also one of the possibilities to looking into and making a new system. So what do we do about it? There were no applications at that time, and we did not have a quantum computer at that time. So there wasn't much developments for the next decade. So in around 1991, in came the very first algorithm that actually showed that there is some possibility for a huge speed up. So previously, due to Richard Feynman's discussions, which you can find it online, it was rumored to believe to just be useful for quantum simulations, right? Simulations of your molecules, your drugs, whatever. But then came Diosh and Josa, which started with one of the first quantum algorithms to show a significant speed up. So it was a toy problem. It didn't really give you a lot of insights. So this basically classified whether a balanced or a fixed function, whether a function is balanced or fixed in like constant time. People still were not interested in it. People were like, okay, fine, it's a toy problem. There's no real use for it, right? So what do we do? Nothing's done. What basically changed everything was this man. So you might have heard of the Shor's factoring algorithm. Peter Shor at Bell Laboratories in 1992 basically theoretically showed that you can decrypt applications, which is a huge deal because at that time, and even now, a lot of encryption is based on RSA. The very fact that RSA is pretty difficult to crack is the reason why it is used for encryption. Because if you were to use a normal computer, your laptop, it would take billions or even trillions of years, right? So this theoretical proof kind of got everyone into the discussion as to quantum computing. Okay, now there's a really good use case here, right? What is there any other place we can look into? This is where the traction basically started when Peter Shaw came up with this algorithm. So get it right. The RSA 2048, which we have right now, is very, very strong. So if you were to crack it with, let's say, a very huge supercomputer, 47 billion years, that's the statistics. So I just told you that we are getting a really exponential speed up, and people got excited with this Peter Shaw's algorithm. How much of a speed up are we talking? So a recent statistic, just 8 hours. So a calculation that can be done on a very big supercomputer in 47 billion years. And mind you, it is based on your approach of calculation. You can even, there are some estimates that are 300 trillion years. I'm taking one of the best case scenarios here. We are getting it in just 8 hours. So you can see that this is a really, really exponential and interesting result, which is after which a lot of governments started to invest and got interested into this computation. Is there any other? Is there any other? Uh, im- uh, is there any other demonstration of the same? So let's just see what happened after this. Basically, a lot of uh, a lot of advancements started taking place. So we have a lot of demonstrations that came up. So we have the very first demonstration of factoring in 2001. The first computer came in around in 1998, and 2001 IBM kind of demonstrated that yes, we can factor something. And we have D-Wave 1, which is one of the first commercial quantum computers which came in 2011. Google uses it for a lot of their applications. And we have the world's first openly accessible quantum computer. That's the IBM Quantum Experience. It's like a cloud platform where we can basically access the quantum computers. So yes, right, 2001 we have demonstrated factoring, and it kind of gives you a big speed up from 47 qubits to from 47 billion years to 8 hours. So it's pretty much powerful. We can do lots of stuff with it, right? Turns out it's not that simple. So if you were to add something on a quantum computer, a classical computer or your normal laptop would take like 0.0075 milliseconds. It's a statistics I pulled out from one paper in 2009. This is 2021. We have even more faster processors, right? But a quantum computer would do it in 75 milliseconds. And while 75 milliseconds is short, yes, but if you see, it's a huge difference. You are talking about an exponential. You're talking about basically an exponential change, right? So, okay, Vishal, okay, you just told me that the quantum computer has an exponential speed up, and now you're telling me that the quantum computer is slow. What do you mean? So it actually depends. The answer kind of depends. So what does it depend on? The idea here is quantum computers are useful and again give exponential speedups for very specific calculations. So the idea here is you have to model your program, you have to model your problem in a way that can make use of certain tools. And what are these tools? Is quantum superposition, entanglement, and interference. So if you see, a quantum computer can do what a classical computer can do, but it does it in a very inefficient way. So you would want to use a quantum computer where it does its work the best, right? So there are certain phenomena in quantum physics which a quantum processor can exploit, and if we model the problem in that way, we can basically exploit it and get our result out. So let's talk one by one about each of these. So we'll be talking about these three basic tools which we have, which enable us a new paradigm of computing, right? So we are given a possibility to think in a different way to approach the problem, right? So the first one is quantum superposition. So the basic idea of a superposition is, let's say we have a classical bit a normal bit which we normally have two values, that is 0 or 1. But when we are talking about a quantum mechanical system, it does not just have 0 or 1. It has additional information in it. So we are basically having a superposition of states. We are basically having a combination of all possibilities within a single qubit, right? So we are not just having two values here, but we are having a spectrum of states right now, right? So which can immediately give you a kind of an application is parallelism, right? So because you can store one qubit in many states, you can compute information in many states. So if you were to compute in a classical computer, let's say if you have a 64-bit computer, it can compute 64-bit strings at a time. Okay, but if you have a quantum computer, because a qubit can stay in multiple states, and because it's a qubit, so two states, you have 2 raised to 65 states of information. So the formula here is 2 raised to n, right? So if you have a 3-qubit computer, it's 2 raised to 3. If it's a 64-qubit computer, you have 2 raised to 64 states of information, all which you can process at a time. Remember, I'm talking about information. We are not breaking any information theory principles here. You can process 2 raised to 64 states, but you can only obtain 64-bit of information, even from a quantum computer, right? So the main word here is you can process a lot of things parallelly. And also the scaling thing, let's say if you want to scale a normal computer, a 64-bit computer, a 64-bit computer will kind of process 2 times the information of a 32-bit computer at the same time. But since here we are talking about something that is raised exponentially, a 33-qubit computer will have 2 times more informational processing capacity than a 32-qubit computer, because when you have 2 raised to 33, it's double of 2 raised to 32, right? So as you can see, because of this, we can have like exponential computational capacity. Remember, I'm talking about computational capacity, not access to information, right? So let's talk about the second tool, which is quantum entanglement. Okay, so quantum entanglement is also a weird phenomenon that was noticed in these quantum physical system, in quantum mechanics. So the idea here is, let's say you have a normal bit. What happens if there are 2 normal bits, they do not really have any correlation, right? If one is 0, one is 1, and you have them separate, do you have any correlation? No, they do not really have a correlation with this. But as it turns out, there were experiments done there's something called as the Bell state experiment. What basically happened is, when you have 2 qubits, a quantum mechanical system, let's say when you have 2 qubits and you process it in some state, there appears to be some weird correlation between them. So even if you process these bits and then you throw these bits somewhere different places around the world, right? You keep one bit somewhere, let's say in one part of the universe, and one bit somewhere in your hand right now. If you were to do something on the bit in your hand, it would cause some change in the bit that was on the other side of the universe, right? Which is kind of weird because you have not connected it with something, but there is still a weird correlation there. So this is something that is being exploited in a lot of algorithms, right? So we'll talk about one of the application in the later part of the slide, but this is one of the most important, interesting fact that is being exploited in quantum computing applications. So this is one of the tools which you have in your hands. And the next part is, we'll talk about the last tool which we have, not the last, but one of the most important tools is quantum interference. So I talked about quantum superposition to be a qubit being in multiple states at a time, right? Quantum interference is basically something that drives you towards getting an information. So I mentioned that while we can compute information, we cannot gain the information we cannot gain the same amount of information, right? So if we have a 2 raised to 64 bit system, we can work with 2 raised to 64 bit states, but we cannot really get 2 raised to 64 outputs. We can only get 64 bit outputs. So now the idea is that there are so many states, and you want to somehow smartly manipulate the state in such a way that you get your information from those 2 raised to 64 bit states into 64 bits. So that's where we use interference. So what you do is you apply gate operations to basically drive the quantum state into what you want it to be, right? So you drive the concept, the information into the state, and you get the usable output later. So how do you do that? Well, you do that using something called as a quantum circuit. So right now it's in the state where you have circuits around. Okay, so we are still working with on the circuit level. If you see a lot of the programming languages right now, not on a bit higher level as we work with other programming languages, the classical programming languages. So the idea here is we basically apply these gate operations, which kind of interfere with the state and drive the state to what you want. And then you get measurements out of this. So if you can see, these single lines are basically the quantum data, which is stored in something called as qubit, which I'll come to later. And then these double lines are classical data, because you want to use the quantum data in your real life, right? And right now everything is classical, so we cannot do much with quantum data. So what we are doing is we are basically passing it to classical data using measurements. I'll come to that later too. So double lines are usually measured and usually denoted as classical bits. This snippet is of a programming library called as Qiskit, which I'll come to later too. And this might be a good time to explain you about what is a qubit, right? I did mention about qubits. What are qubits? So basically, it's like a quantum mechanical analog to a classic bit. So your normal bit has, your classical bit has 0 and 1. A qubit also has 2 states. So we are calling it like a 2-level quantum system, right? So apart from staying in the value of 0 and 1, it can also stay in values between 0 and 1. So the sphere which you're looking here is what is called as a Bloch sphere. And when you want to denote a state here, you basically pass in array and set the angles to denote the state. So the state up here is 0, and if it goes down, it is 1. Anything in between are also states, but they are states in between 0 and 1. So do you realize what I meant by multiple states? So you can have this point anywhere on the sphere and it will denote a state. So that many states we are working with, right? So now we have, we talked about qubit, and so what do we apply on the qubit, right? I talked about the interference. So we apply something called as gate operations. So gate operations are like building blocks of a quantum circuit, right? Even our classical circuit, we have like gates, and gate, or gate. The similar way, we have certain gates, certain basic gates for a quantum computing system, right? So we have something called as a poly X. So it's called as a NOT gate. We have a poly Z. It is called as a phase flip gate. We'll come to that later. We have a Hadamard gate. This is a very important gate. Basically, if you apply Hadamard gate to a qubit, it puts it in superposition, right? And we have a CNOT gate, which is also called as an entangling gate, right? So the part to remember here is quantum computing is kind of reversible. It is reversible. All these matrices are unitary matrices. They are unitary operation, and all these operations are reversible. Meaning, if you were to not measure anything, you can traverse back any time in the circuit to get back your input, right? So that's one basic thing about quantum computation that you should be remembering, that everything is reversible here, right? So the next thing is, okay, you have applied your gates, You have applied your circuit on your qubit. Now you want to get your measurement out. How do you get your measurement out? Basically, you apply a measurement operation. So you basically define measurement in a quantum mechanical system as testing or manipulating a physical system in order to get a numerical result, right? The thing is, when you observe or you measure a quantum state, you collapse it to either a state of 0 or 1. So what basically happens is, I told you before that a qubit can stay in states between 0 and 1, or have many different states, right? But when you apply a measurement operation to get usable output out, you collapse it to a state of either 0 or 1, right? And there is a specific probability related to whether it would fall to 0 or 1 depending on your quantum state. So that's the problem here. When you measure, sorry. Okay, so when you basically measure something, you're basically collapsing the quantum state and you are decohering it, right? After measurement, you are losing everything what you have. So this is not really a quantum operation, right? So this is something you have to be careful about. You measure always at the end of the circuit. Most of the time, you can have mid-circuit measurements too, but you usually measure at the end of the circuit to get your usable output out after you have basically applied your quantum gate operations, right? So, well, we have talked about measurement now. We now know that, okay, when we measure, we get some output out. So what are we measuring on? What are we making our circuits on? What is the physical device? There has to be something on the back end, right? So let's talk about what types of quantum computers exist, right? So there are quantum computers that are currently made right now. So you have quantum computers from IBM, you have from Google, you have from a company called as Rigetti, you have from a company called IonQ, Honeywell. So all these have different types of quantum computers right now. A lot of these are accessible even now. So I'll show you about the IBM quantum computing access thing. But yes, a lot of these are accessible through cloud sources. So there are a few types of quantum computers that you can be finding right now, because right now we need to define how a qubit will work, right? So there's no gold standard here. There are a few different types, and every type has its own plus points and minus points. So you have something called as superconducting qubits. That is what IBM uses. Basically, as it says, you are having a superconducting Josephson-Johnson, which is kept at really low temperatures. Okay, I'm talking about almost 0.15 millikelvin. You use something called as a dilution refrigerator to keep them at so low temperatures and basically make them behave like a quantum mechanical system. And this is what is basically a superconducting circuit. It is usually used in using your semiconductor based chips. So this is one of the types. Then we have trapped ions. You basically trap ion in one of the lattices, and you get you can measure the spin in vacuum, and that's how you get the state 1 or 0. Next is a photonic computer, which is kind of a hot topic right now, because while all these types of computers need like very sub-zero cooling and like a vacuum kind of condition, photonic computers basically can work on your room temperature. So they work using wave-guided lasers, right? So the idea is basically you can look at the phases and get your state out. So this is one of the type which is being done in a lot of countries in Europe. So Europe is pretty much into photonic computers. A lot of hardware bases are even set up there, hardware startups and stuff. Then you have your silicon based. So basically you are checking the nuclear or electron spin of a doped atom. Here we have P and Si. We have different types of silicon based. This is not really that common. And then we have something which is Microsoft is kind of working on, is called as a topological qubit. So this basically uses anions or fermions to kind of get the states out. This is a theoretical model, and people are very excited on it. I'm personally excited on it because this allows to scale very, very easily. So they use something called as Majorana fermions, which is not yet discovered, but they are feeling they could discover it. And I mean, I am on the optimistic side, right? So yes, so you're saying, Vishal, there are so many type of computers, there's so many companies investing and doing on this. Surely we are on the pathway of using quantum computers everywhere, right? Bye bye classical computers, bye bye mainframes and stuff, right? No, it turns out there are a lot of challenges now. So the experiment that I told on 2001, it just factored the number 15. So that's very, very far away from a 2048-bit RSA encryption, right? So what are the basic challenges that we have right now? So fragility. A qubit is very, very fragile. So when you are applying the gate operation, let's say even on cloud, when you're coding something, it's very fragile. And when it's being carried out on the back end, even if there's a very small disturbance in the environment which is in, be it radio waves or even temperature fluctuations, the state which you want is gone. Suppose you want one, you won't get one, you will get something else. So this is one big challenge, noise. That is the one of the biggest challenges in quantum computing right now. Most of the time when you pass in a state, you have to do a bit of post processing or smart algorithm planning, right? So you have to have some noise mitigation or error mitigation on a software level and a hardware level to get some usable result out. Then you have decoherence time. Basically, a qubit is unable to hold its state. So in our normal computers, when you have like state one, it will be one most of for a long while, right? I mean, until you remove the voltage, it will be one. So it's not with qubits. The state they can hold is in nanoseconds. Some of them are able to hold 10 minutes. But yes, basically you have to have your calculations or your operations short and sweet. Otherwise, you won't be getting any information. And then error propagation. So what basically happens is when you apply gate operations, you have to basically use lasers, or you have to use something to rotate the qubit or get the operation on. What if there is an error in it? Let's say there's an error of 1 degree or 10 degree in that rotation. What happens when you have like a million operations? That 10-degree error will cost you a lot. And since this quantum state can have so many states, you will end up somewhere where you do not want to be. So that's also one thing. That's also one challenge. And expensive hardware. You cannot really go out and buy a quantum computer. You need a big dilution refrigerator, a very big space. So it's kind of like the time of 1960s when we had like room full big of your mainframe computers. We are kind of at that stage right now, right? So we have challenges right now. Still, you might say, hey, okay, you hyped me up with the Shor's algorithm thing, and you told me, okay, there are so many things, and now you're telling me that nothing works out. What's going on? It turns out there are still applications with this. Okay, we are at an early stage. The first commercial ones at least came out around 2011, right? So we have to give it a bit time to um, develop. But still, there are a lot of systems right now which we can use, and there are a lot of companies right now which are also making use of it in a lot of problems. Right? So basically, the current applications which we have is a lot of there are a lot of applications right now, but this is just summarizing a few of them. Please do not think it's just these. It's kind of an unlimited possibilities, but yeah, I'll come to that too. So right now, the first main thing, as Feynman said, was simulating physical system. What's best than simulating chemistry, right? So simulating your chemistry molecules basically are quantum physical systems. It only makes sense to kind of simulate a quantum physical system natively on a quantum physical computer, which is a quantum computer. So what it means for you is you can simulate new types of chemicals, new types of materials, and a lot of you can observe a lot of new properties in the chemicals which you previously could not, because there is a lot of computational overhead if you want to simulate this. No, and not everyone can afford like a big supercomputer like IBM Summit. Right. Next is optimizations, which is mostly right now it is used. So the computer which I told you, D-Wave, which Google is using, is being used by a lot of companies. So optimizations would be your supply chain optimizations, your traveling salesman problems, or basically something where you have to uh, determine certain pathways to certain resources, right? So optimization problems are something that's being very much looked into, and I'm personally looking into one of the projects of optimizations in supply chain. So it's something very interesting. Machine learning. Machine learning is also kind of something which quantum computing is used into right now. So if you are working on machine learning right now, this could be something which you could consider, right? So quantum machine learning is something which is also being developed. So it's kind of like a hybrid model. You have your classical model too, but you are also adding in um, uh, your 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 quantum functions inside, so that you have like a hybrid model of a classical and a quantum computer together to get your results out, and results are a lot more promising. Okay, so there are natively complete quantum machine learning implementations too, but you can start with the hybrid models. Material science is also very interesting. As I told, materials are also quantum mechanical. uh, you can look at them as quantum mechanical systems, and right now when you simulate them, you have to convert them into mathematical models and then uh, process them and get your output out. So why not skip the middle part and directly just put this thing, right? So yeah, it's not as hand wavy or easy as I am saying, but yes, this would give you much more faster or better results. And unknown problems are basically, here's the thing, this field, the IBM has basically released their quantum computer in 2016, mainly because they have a quantum computer but they do not know much what to do about it, right? So since this is kind of on the newer side, a lot of the possibilities have not been experienced yet, right? You have these three tools: superposition, interference, and entanglement. It's up to people now to find ways to manipulate this and apply, right? So that's why always I say that the people in this room could be the next huge person, the next big person, or the first person to get an algorithm out for one of the applications which we have not yet seen in quantum computing, right? So there are still a lot of headroom and possibilities in this, which is what is kind of exciting about this, right? So there's also one more buzzword which you might have heard in a lot of places: quantum teleportation. So I'm pretty sure you might have heard of this in a lot of uh, blogs and posts, and they overhype this thing, right? So trust me, this is not teleporting something up. So you cannot just say, Scotty, beam me up as of yet. And I do not think you can do with this. Might be another approach for this. But what you're basically doing with quantum teleportation is you're transferring quantum information. Okay, you're transferring quantum information without physically transferring a bit, right? You're not really transferring a qubit. I'm sorry, not a bit, but a qubit. You're not basically transferring the qubit, but you're transferring the information in the qubit using entanglement. So this is kind of the circuit for it. So the idea is, let's say I have two qubits here, and you remember the thing I told about entanglement, we can prepare them in a certain specific state to get correlation out. Let's say I entangle these qubits and then I separate these out. Let's say I take one myself and give somewhere one to somewhere in the satellite, right? It's a this qubit is in the satellite now, right? And one qubit is in my hand. So let's say this qubit is in the satellite, this qubit is in my hand. So the idea is, if I do certain entangle, if I encode my state, which is this state, inside what the qubit which I had right now, what will happen is, using this teleportation protocol, the qubit which was in the satellite will have the state which I encoded here, and I do not have to send any qubit here. Yes, I have to send the measurement results out, but the measurement results out are just 1 and 0, and the quantum state is a very complex state. So I'm just sending a few binary strings, and I'm getting a complex quantum state somewhere in the other place of the world, or in this case, we are in the space, right? And I'm not really transporting a qubit anywhere. So this was demonstrated by the Chinese first. So they basically transported the information from a satellite which was in orbit 1,400 kilometers above. So as you can imagine, this is kind of difficult, because even maintaining the entanglement between these states is kind of difficult, right? So as long as you can maintain, you can use this, exploit this to basically transfer states between each other. Now you might ask, okay, why are we doing this? Can't we just, copy paste? Turns out, no. So in quantum mechanics, we have something called as the no cloning theorem. So in a quantum computer, you cannot really directly copy paste stuff. Okay, no control C, control V, because what happens is, if you remember when I said about measurement, it destroys state. So to copy something, you have to see it to copy it, right? So when you see it, you're measuring it and you're destroying the state. So what are you going to copy? So that's the main idea behind it. You cannot really copy anything. That's why you need tricks like this quantum teleportation protocol to kind of swap states in between, right? Now you might say, okay, no one can copy it and you can't really see it. What's one of the good uses for this? Cryptography, right? You do not want anyone to see your stuff in cryptography, or you want to at least hide it in a very good way. So this is basically the best. This is the best place for cryptography, because when you have a quantum state, if you want to send, let's say, a public key across, if someone were to tamper on it, I mean, you cannot really stop it, but at least you'll know that someone is eavesdropping on that, right? And then you can take measures. So the secrecy is really guarded using, let's say, a quantum channel. That's why a lot of investment is being done in these quantum key distributing, quantum key distribution, quantum key distribution stuff, and a lot of new modules and startups are coming up for quantum cryptography. And there's also this term which you might have heard, that's called post-quantum cryptography. So basically, after it was found out that the RSA could have been cracked, there are also other algorithms like Grover's algorithm that significantly brought down the security level of a lot of standard algorithms. So you have something called as post-quantum cryptographic algorithms, which are basically classical algorithms which basically are safe from these quantum computers. They cannot, even if the quantum computers were scaled at a huge scale, we cannot really crack them. So that's also one thing. And we have to also keep this in mind, that right now we are just at 65 qubits. So okay, you might have heard some systems of like 2000 or 5000 qubits. They are from D-Wave. They are called as annealers. They're not really real quantum computers, or they are a different breed of computers, but they are very specific. But if you're talking about the general purpose quantum computers, it's just 65. And we are hoping to have a 133 qubit one in the next year, and a 1001 the year preceding it, right? So yes, this is something that we have to look into. There are so many applications of this, and there is basically so much possibility with this, because not every field has been touched right now. Not everyone has used the tools which I have told to right now go into every field, because not everyone is exposed to this field as much. And also one more reason might be because, yes, since we do not have that much big scalable systems, we cannot really demonstrate a lot of the benefits which we are proclaiming, right? But nevertheless, there is huge investment going on. This is a this is a statistics from the starting of 2011 21. So India itself has been uh, pledged to basically invest 8,000 crores on this, and there's huge investment in Europe. So you have this Munich Quantum Valley project, the Quantum Silicon Valley project, Munich Quantum Silicon Valley project, and then you have Australia investing a lot in this. So you have very many coalitions found where they are working specifically on getting results out. And then you have also China heavily investing on this. You have USA also investing heavily on this. You have your companies like Honeywell and IBM from USA, which are investing and developing systems. You have Google also making their own systems. I mean, they have not given it open access right now, but if you're a researcher, you can access that. Microsoft finding their Majorana fermions right now, and that is also a huge uh, task for them. So it's not that uh, it's uh, it's not picking up pace. It's picking up a huge pace, and a lot of people are interested about this. So this is a really good time to get on with this, or at least keep this at the back of the mind when you're doing uh, let's say applying something, that maybe there is also another way to approach your problem using quantum computation. So that's the general idea of this. So basically you can have a lot of speed ups, or at least a different way of approaching a problem. So where do we come here? So this was, as I told in the starting of the session, an introductory kickoff session for SoSC Quantum. So the main idea and the main goal of preparing this group was to create awareness about quantum technologies, right? Just want to spread the word that yes, this exists, and this could be something you can keep in the back of your mind, or even inspire you to get into this field as a career itself, right? Another thing about SOSCQ is we are aiming to have like a safe space for self-learning. So all like-minded people or someone who's interested in quantum computing can come in, safely discuss his ideas, and he can not really fear failing or anything. There's nothing kind of failing here. You can basically have whatever ideas you want to speak up, or even if you're making a mistake, there will be people helping you out. So, and there is nothing kind of a set leader in this. So this is kind of a community driven model. So if people want to do something, if the whole community wants to do something, we can come up and definitely go in this direction, rather than having a single guy handling everything or dictating something. Remember, this field does not have a fixed path, and this is so interdisciplinary. Like basically anyone from any field can do this. I've seen applications ranging from quantum chemistry, quantum CFD, quantum materials, quantum music theory. So there's literally people from everywhere around the world that are coming in, right? So that's something that's beautiful about this. You can have you can be of any field, and you can come in and contribute something to it, right? Because there might be an application which might not seem possible but could be possible. That's how Shor's algorithm or any other algorithm was kind of started off as, right? So I have told you about a short introduction at least. So the recording will be sent, of course. You can watch back again, or if you have any doubts, you can contact again. So what to do next from here? Like suppose if you are interested now and you want to learn something on it, what to do next? So I would highly suggest you start from this library, Qiskit. So Qiskit is a library that is provided by IBM. It is supported by IBM. It's an open source library. And the reason why I advocate or I support Qiskit is because it's one of the most common and the most widely used libraries right now. So this is something which I guess everyone in the quantum computing sphere has started with. So because of this, there's a huge community built up around Qiskit. So the thing is, when you're learning something new, if you stumble or if you have any roadblocks, the community can help out, or you can find resources very easily to basically to to overcome the roadblock, right? So that's why you can start with this Qiskit textbook. So it's like a textbook that is completely made with like very nice uh, segregations of each chapter. It will start with your basic gates, your basic um, starting point of how would you start, how would you look for things, how would you approach problems. And I mean, there are also code samples there and labs, and it's regularly updated, it's community updated, right? So you can have you can also contribute from your end, which is what I was planning to do for this summer. Maybe contribute one of the chapters in this book, right? So the prerequisite is, of course, a bit of linear algebra. You need to understand how a little bit of linear algebra and complex numbers, and then I guess you should be good to go. If you're all engineering students, we have had this in the first semester, so this should be good to go. Then let's say if you're a VLSI guy, if you like to design circuits, what if I say that you can design your very own superconducting chip right now? So Qiskit has made this super awesome thing called as Qiskit Metal, where let's say you're an electronics student, you can design a superconducting transmon chip right now, and it's a GUI based interface, so it's like either drag and drop with very minimal coding, and it's integrated with ANSYS HFSS, so you can get your simulation results very up. This is one of the projects which I had done for a hackathon. It's kind of very easy to get on board, right? So if you are a VLSI enthusiast, or if you like to design stuff, this is where you go. And the best part is you can export your chip into a file ready for fabrication, into a GDS file, right? So that makes things easier. Now, next, say you are a machine learning enthusiast. You want to see how is it useful in machine learning, or can you go around with it. You have Penny Lane's Xanadu. So these guys are kind of on the forefront of quantum machine learning. So they have like a library where you can have and a lot of tutorials where you can integrate machine learning code with either purely quantum models, or you can have a hybrid model based. Okay, just to also say that Qiskit also has a module called as Qiskit machine learning, which also has hybrid and purely quantum machine learning model. So, and there are a lot of tutorials. You'll love that, right? And if let's say you are a TensorFlow user, why not use TensorFlow Quantum? So TensorFlow also has a quantum backend which works on something called as Circ. Okay, so like IBM has Qiskit, Google has Circ. The reason why I did not recommend it is because it has a little bit of steeper learning curve than Qiskit, and documentations are kind of far less than your Qiskit counterpart, right? So I would suggest it's kind of like programming. So if you understand one of the libraries, it's very much likely that you can work with almost all of the libraries, the general functions at least. Of course, if you want to have specific functionality, you will have to learn about that separately. But yes, if you are learning Qiskit, if you get the idea of Qiskit, I'm pretty sure you can do with Circ. Or let's say Microsoft has their own called as Q Sharp. Then you have Huawei's Project Q. There are a lot of other libraries there, right? So links are also there. I'll be sharing the presentation too, if you guys wish. So that's it from my side. Thank you so much for your time, and I'll be taking in questions now. Of course, you can contact me at the email, or if you can find my LinkedIn, which I'm not bothered. I've not really completed that. So if you find a half empty account, that's probably me with Vishal. So thank you so much for your time. Thank you so much for listening to, and feel free to contact SOSCQ or any of your friends to either join this group, or if you want any assistance regarding quantum computing, we will be there, and feel free to ask your questions.
Yeah, I had a question. Um,
Yes.
Hi, Vishal. My name is Abhishek. A wonderful presentation, by the way. Kudos to you and the team for having this session. I have
Thank you so
three
much.
questions.
Mm-hmm.
that I'd like to have a better idea of what SOSCQ stands for. So,
Yes.
as a student, uh, first of all, I'd like to know you because
Mm-hmm.
you are leading the initiative. So,
Mm-hmm.
I've heard that you are a part of a couple of open source communities already
Mm-hmm.
and have worked or performed on hackathons. So, could you
Mm-hmm.
just let me know uh, what have you done so far in terms of leading the community on quantum computing initiative?
Definitely. So right now, what I thought was basically most of the knowledge I get is not really something I've paid for. I'm not even from the computer science background, right? So everything I've got is from the community. So this is something which I wish to give back to, right? So this is how I kind of started giving back as I was learning. So I got to know about this field in the pandemic, kind of right around March, I guess. And I got hooked on with IBM quantum challenges. So the first challenge that I had come across was around August. So we had sorry, not August, we had around November. So um, it was a quantum challenge where we had to complete a few exercises to get a certain batch, and I had got uh, an advanced level batch, which was the flagship batch there. And after that, I joined a few communities called as Q World. So Q World is one community which is right now leading in uh, giving quantum education in developing countries. So countries like Estonia, Turkey, or Latvia, or stuff like that, where people or Zimbabwe, Africa, places in Africa. So where communities are just growing up technically, right? So what I do is basically I mentor in workshops there. So they have workshops called as Q Silver and Q Bronze. Guess I can show you the website. Give me 1 second. So yes, this is the website where basically you have something called as Q Cousins, and you have these many countries on board. There's Q India too, but I directly work with Q World right now, and they have these workshops called as bronze and silver. So bronze is for an very introductory level, gives you an initial idea of what is quantum computing, which I would suggest anyone to join. I would definitely post the next Q Bronze event. You'll find me there too. And you have something called as silver, which is the bit more advanced, where you have, let's say, um, you have a bit more advanced algorithms like Grover's, and you will also be working with Shore's algorithm, the algorithm which I told there, right? So this is one community I've been working on, and there's this Q education department that makes educational material. I also contribute there. I give my time there too, so that people can, to make better material. Right now, we are working on a new framework that is called as Project Q. So that's something we are working on right now. And yes, I do give small talks or workshops wherever it's needed. I do not have like a fixed community. So I thought that, okay, I have been contributing everywhere. Let's contribute around here too. So that's it.
Yeah, good to know, Vishal. Good to know the community is in good hands, and looks like you have experience in handling workshops previously as well. And glad you're also part of several other communities. My second question is, as a student or a person looking to join SOSCQ,
Mm-hmm.
what are the things that they can expect to get out of it? Because let's just say I'm a fresher, I just joined first year, and I heard about SOSCQ.
Mm-hmm.
Now, because the theory and the knowledge that was presented has been there for the last decade or so, because even I've worked on quantum computing and I've built projects on quantum computing
Mm-hmm.
regarding quantum cryptography, which most companies in India just base on that. And because most technology is backed, at least limited, by the providers such as IBM and Google,
Mm-hmm.
because they provide the underlying hardware for to make everything work, and the research is still ongoing.
Mm-hmm.
So, what would you suggest for a person or a student joining SOSCQ to look forward to on their journey to in quantum computing? Should they be looking at white papers that they can write? Should they be looking at projects that they can build, or should they be looking at just understanding quantum computing, but knowing that the future implications is still a bit far ahead into the future, or they have to go deep, really deep to actually start with something groundbreaking? So, as a student who's a fresher joining in, how would you tell me that what I can get out of SOSCQ?
Yes, so SOSCQ would kind of give you, okay, so you cannot really have dictate someone to have a certain learning path, but would at least would expand your vision as to what all things you can get into, right? And using that knowledge, you can make your own projects, you can make your own hybrid projects, or you can make your own pure quantum projects too. White papers, I wouldn't say as of yet, because I don't think even I am that qualified to do direct white papers. But yes, you can have your. So as I said, it is also community driven. So the community can say what they exactly want. So if they want a flipped classroom to read up some textbooks, they can have that general knowledge. Or if they want to team up in groups for hackathons or any events, because any event will also be posted in the Discord server. So yes, there will be a Discord server that will be made and circulated to all, which you can happily join. So as a first year, you can expect exposure to where you can learn and what you can learn and where you can apply. So as Abhi said, yes, it's kind of limited right now with the backends which we have, and we cannot really have real world applications that give you very concrete results out, but at least you can be ready for what's coming. So when let's say in a decade or 5 years or a decade, I'm pretty optimistic about that. If you're in the first year, you're kind of in a very good position because uh, you're already exposed to this, and you can also incorporate it along with what you're doing right now, right?
Thank you so much, Vishal. As I've said before, the presentation was very insightful and well paced, and I think this initiative is going to help out all the Sayadrians and anyone who's interested a lot. And I'm
Mhm.
glad you took up the initiative. I'll be keeping a close eye and uh, trying to stay as connected as I can to this field. And thanks once again.
Thank you so much. Thank you so much, Abhi. Any other questions? Okay, so you mentioned some cases like addition classical computer is faster than quantum. Is it because classical algorithms are based, so we need to find? Um, so that are based on bit manipulation and Boolean algebra. So yes, so the way classical computation happens is kind of different than quantum computation, right? So you can basically use your quantum gates to mimic addition or any other classical operation, but you need to understand that most classical operations are non-reversible. So you want to have a reversible counterpart of your non-reversible operation. So that's where you lose some headroom. And yeah, you need to so to find a speed up, you need to use those specific tools which I told. So to get a speed up out, because you're using a different paradigm or a different approach than classical step-by-step approach, right? I hope that answers your question. So okay, so we have one more. Entanglement sounds magic. How are qubits? That's one thing that no one has. Shrujan, can you mute your mic?
Oh, sorry. Yeah.
So that's one thing which no one has understood completely, right? So even if you ask a PhD or a postdoc in quantum physics and ask him, okay, how does quantum mechanics work or how does entanglement work, you'll get the answer, even I don't know. So that's the thing. It's kind of like magic, which is why Einstein kind of disregarded that theory. And if you would see, there's a very famous paper on the EPR uh, paradox where he said it was a spooky action at a distance, but it was later found out by Bell that yes, this actually exists and there is a experimental proof for it, right? So how are we? How are the qubits? Okay, so Qiskit is like a programming library. It's like a programming library. So it's like a software layer, right? So you need to work with a backend. So the backends here is usually, if you're talking about Qiskit, is IBM Quantum. IBM also, Qiskit also has integration with other backends like IonQ um, or I guess even with Honeywell. So what basically happens is when you make your circuit, it gets transpiled down into something which the quantum processor can understand, and then you pass it along the instruction in pulses. So you have like, if you're talking about IBM Quantum, you're talking about microwave pulses there. Okay, so entanglement is basically, if you're talking on a hardware level, is done using something called as couplers. So on a chip level, you couple those qubits and get the correlation out. Okay. I hope that answers your question. That's a good question. Okay, so next week is kind of internal, sadly, or I was about to start an introduction with Qiskit, but we'll see the session, the week preceding that, we can have an introduction to Qiskit, at least the starting part, where I can show you how it kind of works, or maybe even get you like a demonstration with an actual quantum backend, so that you can see about what I was talking about, the noise part. So yes, if there are no questions, you can always email me or contact your SOSC friends, or you can contact me too if you have any questions. We will have the Discord server set up. The Discord server links will be sent to you via email, and you can join in and also ask your questions, and any updates that I get regarding any events or hackathons, I'll definitely be posting in, and everyone can be posting in their stuff, and we can also talk about what to do next as a community, right? So thank you so much for your time. Thank you so much for your questions, and thank you very much for sparing your time for this.